Okay, let's say a little bit more about the wave function psi. It is a function, obviously, of real variables. R is real, x, y, and z, or whatever coordinates we're using are real variables. T is real, but psi can be complex. It's a complex, in general, a complex function of real variables. As you might imagine from when we solve the Schrodinger's equation, it's got complex terms in it. So what is it? Well, we called it a wave function. It's also been called, psi has also been called a matter wave. Max Born, the physicist, called it a guiding field, and Einstein called it a ghost field. So how do we interpret it? Well, it's hard to know how to interpret it all by itself. In fact, what we always see in the way it's used is in terms of its complex conjugate in combination with psi. So psi star psi. Psi star times psi. Well, we know from complex arithmetic that this is equal to the square of its magnitude, which is then purely real. We understand this to be a probability density. And this is the probability, this tells us the probability of finding a particle in some region of space. And since the particle is assumed to exist somewhere in the universe, then if we integrate over all space, so this is the volume integral of our probability density, that integrates to 1. So this is a statement that the particle exists somewhere. So the integral over all space of psi star psi, or psi squared, the magnitude of psi squared, is equal to 1. Now, there's also, we talk about observables, like position, momentum, energy, and we mentioned that we find the measured values, or some measurable values, from something involving psi and those observables operators. So how does that work? Well, it's like this. So once we've got psi, we haven't solved for it yet. What we'll do is we'll solve Schrodinger's equation for psi. We'll have some boundary conditions, which we'll talk about. We'll solve Schrodinger's equation for psi. And once we have psi, we can find everything else that can be found about the particle and its properties. So we have a probability density, and as you recall from statistics, there are things called expectation values. So when we talk about observables like position, momentum, energy, we can only talk about their expectation value. That would be a real number that is really the average value that we can measure, average in a statistical sense. So in general, the expectation value of an observable and let's call that observable, we'll use this kind of notation for the expectation value of the observable f. So f is my generic observable. It could be x for position, or r for position in 3 dimensions. It could be p, or p sub x, or e. It's our observable here. This expectation value, the expectation value of the observable f, we find it by integrating over all space. So this is the volume integral again, over all space, psi star times we have our operator for f, f's operator, operating on psi. dV. So integral over all space psi star f hat psi. And this is all we can know about the observable f. So for instance, if we wanted to find the expectation value of position, the expectation value of position would be the integral over all space of psi star position, because this is our position vector. It's also equal to our it's the position's operator times psi dV. Now, the position operator is multiplicative, so it's multiplying what's on the right, but it's multiplicative, so multiplication is commutative, and in this case, we could conclude that this is equal to the integral over all space r, and we have our magnitude of psi squared dV. Now, this is still not going to integrate to 1 because we're multiplying it now times this operator r. All right, so once we have psi, we can find the expectation value of the position. Another example would be momentum. So the expectation value of momentum, showing all three dimensions here, would be the integral over all space, psi star, and we have our momentum operator, psi dV. Now in this case, we can't just move psi back and forth through p because p is a differential operator, it's not multiplicative. But we can go a little bit further and show what the momentum operator is. We have psi star, and we have negative I h bar del psi dV. So we can evaluate this integral and find the expectation value of the linear momentum. Now, once again, I'm going to conclude here and pause after this. We'll use the Schrodinger's equation along with boundary conditions to determine psi. Once we have psi, we can find expectation values of our observables. We'll also find, along the way, we'll find energies, which is itself an observable. We'll find energy levels. It'll all come out very, very neatly. So we'll pick up there.